Okay, so here we have the equation for a chemical reaction known as the Haber process. You should see straight away from looking at the numbers that this equation is actually not balanced. So we need to actually sort this out using the hydrogen and the nitrogen. The first thing I'm going to use is the nitrogen. Reason being, there's only nitrogen on the left hand side here, and in NH3, which is actually ammonia, there is only one nitrogen. So all I need to do is multiply this molecule by this number in order to get the two nitrogens that we need. So I'm going to say 2. There we go. Just get rid of that. Okay, so we've got two NH3s. Now the nitrogen's happy. But what about the hydrogens? Well, now we have 6 hydrogens on this side and only 2 on this side. And how do we get to 6? Well, we times 2 by 3. And therefore, this is going to be our balanced equation. So 3 hydrogens plus 1 nitrogen will give us 2 ammonias. And so that's all well and good, it makes sense, but what does this actually mean? Well, you can think of it in 2 different ways. The first is that if we had 3 molecules of hydrogen and 1 molecule of nitrogen, they would react together and give us 2 molecules of ammonia. And that's absolutely true. But what if, because normally we don't have just, 3 molecules, that would be tiny. So how about defining this in terms of moles? Remember that we said that any substance, 1 mole of that substance will have the same amount of either atoms, molecules, or elemental units, if you like, making up that substance. So 1 mole of hydrogen has the same number of molecules as 1 mole of nitrogen. And both of those also have the same amount of molecules as 1 mole of ammonia. So 1 mole of all of these would be that large number that we saw before, 6.02 times 10 to the 23. But we have the same amount. We just said though that 3 molecules of hydrogen will react with 1 molecule of nitrogen to give us 2 molecules of ammonia. That's an imbalance, and therefore it's not going to be 1 mole reacting with 1 mole reacting with 1 mole. We've got 3 times the amount of hydrogens, so we can call this 3 moles. 3 mole of hydrogen reacts with 1 mole of nitrogen to form 2 mole of ammonia. And this is the most useful definition because we've already in previous videos discussed how we can talk about masses of substances in terms of moles. So we can actually work out the physical amount of ammonia that we can produce by adding in a certain amount of hydrogen and nitrogen. And let me show you what I mean. If we actually did take 3 moles of hydrogen and react it with 1 mole of nitrogen, well, hydrogen, let's use a different colour. Hydrogen has an AR of 1, and we have 2 of them in hydrogen gas, giving us a formula mass of 2. And what we're going to do is that would be the mass of 1 mole. So we want 3 moles, and so we times that by 3, and that gives us 6 grams. So 3 moles of hydrogen weighs 6 grams. Now we have 1 mole of nitrogen gas. The AR of nitrogen is 14. That means that the formula mass of nitrogen is 2 lots of 14 because it's N2, and that would be 28. And 1 mole of nitrogen just weighs the formula mass, and so we are going to have 28 grams. And so even though we are reacting 3 moles of hydrogen with 1 mole of nitrogen, the nitrogen weighs a lot more, 6 grams of hydrogen and 28 grams of nitrogen. Now, this is going to form, I already know what this is going to form because the only product is ammonia, so hopefully this should just be our 6 grams plus our 28 grams, but let's make sure that that's the case. So the AR of hydrogen is 1 and of nitrogen is 14, and what we have is an MR, or a formula mass, of 1 of the nitrogens plus 3 lots of our hydrogen, because it's NH3, so 3 hydrogens. So that will give us a formula mass of 17. And so if we have 2 moles of that, it's going to be the MR times 2. So it's going to be 17 times 2, which would give us 34 grams of ammonia. So 2 moles of ammonia weighs 34 grams. And that did actually work, because 6 plus 28 is going to give us 34. And so it makes sense. We could have worked it out by adding these two together. But this shows you just how to work out the mass of a certain number of moles from a reaction. And the most important point that you can take from this is that the ratio is the number of moles, not the mass in grams. Because we have 3 moles, 1 mole, 2 mole of hydrogen, nitrogen, ammonia. That ratio does not translate to the mass, because we have 6 grams, 28 grams, and 34 grams. That is not a 3 to 1 to 2 ratio. So when we're talking about the ratios, make sure that you remember that it is your number of moles. That means that whenever we're trying to work out how much product from a reaction that we are forming, or how much reactant we need in a reaction, we need to work out the number of moles we need first. We don't just guess the grams, or we don't try and work out based on how many grams there are. You need to work out the number of moles that you need of that substance. That number of moles will then translate to a mass in grams. So let me give you a more complicated example and you'll see what I mean. If we have the reaction, let's say the combustion of methane, so if we have CH4 plus O2 gives us CO2 plus H2O. And if I'm going to balance those, then we're going to have 2 there, because the hydrogens are now balanced. And now the oxygens, we have 4, so we need 2 oxygens as well. So this is now balanced. And now if I said I had 68 grams of methane, which is CH4, and I asked, how much H2O can I form? In grams, I'm going to have to work out the number of moles that I need first. So I'm going to go through this slowly and hopefully you'll be able to keep up. Now 68 grams of CH4, first we need to figure out how much one mole actually weighs. So we have carbon, which has an AR of 12, and hydrogen has an AR of 1. So therefore the formula mass of methane is 12 plus 4 hydrogens, so 4 lots of 1, which is 16. And now to work out the number of moles of methane that I have 68 grams. 68 grams. And I'm dividing by the mass of one mole, which is 16 grams. And that's from here. And that is going to give me 4.25 moles. 4.25 moles of CH4. So that's the first part. If we have a look at our equation, well, the number in front of CH4, we don't have a number there, and that means that it's the number 1. Because 1 lot of CH4 is just CH4. Don't make the mistake and think that that is the number 0, because of course it's not. Now we have 1 CH4 plus 2 oxygens gives us 1 carbon dioxide plus 2 waters. You can think of that in terms of molecules and in terms of moles. And so that means that 1 mole of CH4 here will give us, I'm ignoring the oxygen and the carbon dioxide just because I don't need them for this question, will give us 2 moles of water. So how much H2O can I produce? Be careful, it's not 2 moles because we have 4.25 moles of CH4. So what I need to do is I need to multiply both of these by 4.25. And that will give me obviously 4.25 to 8.5. Because double 4.25 is 8.5. That means that I can produce 8.5 moles of water. And now, to work out the mass of that, I need to work out the mass of 1 mole of water and then multiply it by 8.5 moles. So, H2O. Our atomic masses are hydrogen, which is 1, oxygen, which is 16. These are all on the periodic table, so don't think that you just need to know these off your head. You'll get the periodic table in your test. H2O is 2 hydrogens, so 2 lots of our 1 from the hydrogen, plus 1 oxygen, which is 16. 2 plus 1, that gives us 18 grams. Each mole of, that gives us 18 as the relative formula mass, and therefore 1 mole will weigh 18 grams, okay? If I have 8.5 moles, that means I have 8.5 of these 18 grams. So I need to times 18 by 8.5. And so if you work that out, you are going to get a total mass of 153 grams. So 8.5 moles of water will give us 153 grams of water, and that is the maximum amount of water that I can produce in this equation. So from our 68 grams of methane, I can theoretically produce 153 grams of water. The way I worked that out was by the molar relationships, and that is why it is so useful for us in real life. This isn't just something that you're going to do on paper. In real life, this is used all the time when people need to work out how much of something they need to produce a certain amount of product. Okay, so that's perfect. One thing I would mention is that in real life, you probably wouldn't produce 153 grams of water. This is our theoretical maximum from the equation and from the molar relationships. The reason why this wouldn't happen in real life is because our experiments are never 100% perfect. We never get 100% yield, is what we call it. We'll use that word again soon. We never produce 100% of the product that we could theoretically produce on paper. That's because there will be some error in our actual experiments. There will also probably be some impurities. It might not be 100% pure methane, and therefore we will waste some of the methane which could be used to produce our CO2, And so therefore we probably won't get exactly 8.5 moles of water as we wanted to get on paper. Now, we can actually work out exactly how efficient we have been in a reaction by working out something known as the percentage yield. Percentage yield. And in this case, what we do is we work out our theoretical maximum, like we did in that question just now, and then we have a look at what we produced in real life, and then we compare the two as a percentage. The percentage yield is the percentage of the theoretical product that we actually produced. So the formula of percentage yield is going to be amount produced divided by theoretical. So the theoretical amount that we could produce, and then at the end you multiply that by 100 to turn it into a percentage. And so if I was to use the previous example, we theoretically could produce a maximum amount of 153 grams of water. We carried out this experiment in a lab and we only produced 100 grams. 100 grams of water in the lab. And therefore our percentage yield is equal to the amount we actually produced, which was 100, divided by our theoretical amount we could produce, which is 153. That's going to give us 0.654 to 3 decimal places. And then we multiply by 100. So that's when we're going to get 65.4%. And this is our percentage yield. So I've taken the amount that we physically produced in the lab or in wherever we've carried out the experiment, divided it by, on paper, the theoretical maximum we could make. That gives us this decimal, and then we times that by 100 to turn that into a percentage. And so I hope that has helped. I'm going to be going through some more complicated problems in a separate video because I don't want to bombard you with information all at once. But I hope you can see what percentage yield is and how we work out how much theoretical yield we can get from a chemical equation. So this really does highlight the importance of moles in chemistry, and from now onwards, moles are one of the most important concepts, if you like, in chemistry that you'll face. So very important that you do understand that. So I look forward to seeing you in the next video. We will cover some more complicated problems, so please do take a look at those. Okay, thanks for watching, and I'll see you in the next video.